Hi guys, welcome to another AP Chemistry live stream. My name is Serene, and today I'll be talking to you guys about equilibrium. So I'm gonna first share my screen and kind of show you guys my slides. Hold on, I'm gonna put it on the slides. So do you guys see my slides right now? If you can comment yes, that'll be really helpful so I know that you can see it. Okay. And can you guys hear me? If you can put like a thumbs up or a smiley face, that would be really helpful because I hope that my end is working. Okay, awesome. All right, so how are you guys doing? How are you guys feeling about AP Chemistry right now? I know it's already like the first month into the second semester, so you guys are close to the end. So how are you guys feeling about AP Chem? Are you feeling overwhelmed? I know that like for me personally, acids and bases, that chapter or that unit was the hardest one for me. So if you guys have already covered that, then like the rest, honestly, it shouldn't be too bad. Like I really liked AP chemistry, and I think acids and bases was the one that I struggled the most with, and one that like I had a lot of trouble. Um, I had a lot of trouble understanding conceptually. Um, okay, so I'm gonna go to the first slide. Okay, so are you guys, what chapter are you guys on currently on chem? Because I'm curious. And for those of you who have just joined, I'm currently asking everyone like what chapters or what topics they're currently learning in chemistry. So today we're going to be going over equilibrium, and I want to know if you guys have already covered equilibrium, or just like what kind of things do you already know about equilibrium. So if you guys could like just comment on the chat box and let me know like what chapters you guys are currently on, that would be really great. So that I know like where you guys are. Because I know that like different schools, they move at different paces, and they also cover different material at different times. And I think this time when I was taking AP chemistry, I was doing electrochemistry, so like galvanic cells, and so it wasn't equilibrium, I believe. So are you guys currently covering equilibrium? I'm gonna kind of like give you guys an overview. Okay, my class just started equilibrium unit. Okay, awesome. All right, that's great. So like this stream is gonna be like a overarching, in like a very general overview of the concepts that are under equilibrium. And so this is basically, it's going to build a very good foundation of your understanding of equilibrium. And then do you guys know what the ICE chart is? I think it's the initial and then change and then I guess ending chart, where you put in the different concentrations of your reactions, and then you can kind of like see like how your reaction changes over time, and also kind of balance equations. It's called the ICE chart, also called the ICE chart. But yeah, so like that's like for later. So after you understand the very fundamentals of equilibrium, you can move on to the ICE chart and basically apply it to that. So today we're going to be going over the fundamental concepts of equilibrium, and also if you are taking other AP classes, please do check out our other live streams. We will be adding more on. So we have on Mondays we have math and English streams. We have on Tuesdays we have social science streams. On Wednesdays we have science, which includes chem, and on Thursdays we have history. Okay, and also please do follow our social media at Fiveable so that you can you can stay in the know for all of our future streams. All right, so today we're going to go over, so this looks like we don't have much to go over, but there's a lot of things packed in the slides, or in the, like, there's a lot to go over conceptually. So we're gonna kind of go over an introduction to equilibrium, and then we're gonna talk about the reaction quotient and the equilibrium constant. And then I'm going to also go over like how we can use the reaction quotient and the equilibrium constant to predict the direction of a reversible reaction. And then we're going to go over some practice problems, which is going to be pretty fun. And okay, so first off, to start off, what do you guys know about equilibrium? So if I say something like the reversible reaction, do you guys know what a reversible reaction is? And also, okay, no, okay, that's good. All right, so we're gonna go over that. And also during the stream, if you ever have any questions, feel free to post it on the chat, or put it in the question box, which you should see like on the interface of Crowdcast. Okay, so I'm gonna start. So usually, like, I know that before you learned about equilibrium, before you go into equilibrium, you probably know what like a normal reaction looks like. So it's usually there's like reactants and then products, right? Or equation. There's like reactants on the left-hand side, and then the products on the right-hand side, and then there's like an arrow that points at one direction, right? So the arrow usually it points towards the right, I believe. But in a reversible reaction, there's like arrows going both ways. So it's like, so let's say you have two different cans of like distinct elements, or two different cans of distinct solutions, and then you mix them together. Okay, so what happens in a reversible reaction is that when you mix them together, like one solution is going to produce another one, but then the thing that it just produced, it's going to kind of like rewind itself and kind of like produce the initial solution. So it's like a balanced scale. It's like, okay, I produce this thing, but then this thing produces me, so it's like reversible. So I'm gonna go over that a bit more. So many chemical changes are reversible. So you guys know that physical reactions, they're very reversible. So like from ice to water to liquid, those are all reversible, right? But chemical reactions, a lot of them are also reversible. So, all right, so I'm gonna move on. So this is the sign for a reversible reaction. So it's basically like two arrows. So if you were to draw like if you were to draw two arrows, it would be like you would draw another line down here and then maybe another line up here. But people just like make it look like two half arrows, but this basically means that the reaction goes both ways. So this is an example. So you can see over here we have two arrows pointing in both directions. This is the same thing as this big logo on top. And so this is a reaction of a reversible reaction, or this is an example of a reversible reaction. So so you can see that the reactant, it produces the product, but then the product also produces the reactant. And so it's like, okay, so it's like if you start off with just this, right? You start off with just the reactant, we have none of this. It's going to kind of react with itself and then produce the product. And then as you produce the product's going to start producing the reactant. It's kind of goes both ways. And of course, like the term reactant and product, they're kind of subjective if you think about it. If it's a reversible reaction, it's like either one could be called the product or the reactant. All right, so we're gonna call this reaction rate number 1. Okay, so we're gonna say, or we'll say that the rate of N2O4 to creating into 2NO2. We're going to call that rate, the rate of that reaction, rate 1. Okay, so that is a rate of the reaction going towards the right. And then we're going to call, all right, so I'm going to keep moving. And then we're going to call this the other side going, or actually, so like this is the reverse reaction, right? We're going to call that rate number 2. And so what happens is as you create more NO2 or 2NO2, the rate towards the right decreases as the concentration of reactant decreases, because because the reactant that is pushing the reaction forward for rate number one, or for reaction number one, you could also call it, it is dependent on how much of the reactants we initially have, right? So let's say so like as the reaction keeps moving on, you eventually you'll run out of N2O4. So then you'll have a smaller rate or a lower rate of the reaction number one. But as you are creating more of 2NO2, that is also another reaction in and of itself, right? Like, so that will kind of go backwards. You can see over here this, so you create a lot of this, and then it's going to create more of the thing that you started off with, right? So that is, so like, so as the rate of the rate of the first reaction kind of lowers, it decreases, the rate of the second reaction increases. So it's really interesting thing about this, because it's like, okay, so I'm running out of the initial reactant that I have, but then so then my reaction towards the right is slowing down, but then the product I just made is actually is following another trajectory of reaction, right? It's making my initial solution. So that is basically equilibrium. Like, so the rate is dependent on the concentration of the solution that you have. So let's say you have 0 N2O4, then that means that the rate moving towards the right, the rate of reaction number one, is going to be 0, because you have nothing to react to start off the reaction with. Does that all make sense so far? If you guys have any questions, feel free to just like drop them down below. And I'll answer them as I go. All right, so I'm gonna move on if there's no more questions for this slide. Okay, so I'm gonna go over the rate again. So like, this is rate number one, which is kind of for the reaction number one, and this is rate number two, which is for basically like the second reaction, right, of the reversible reaction. And so the rates of each reaction depends on its concentration. The higher the concentration, the higher the reaction rate. So let's say you have tons and tons and tons of this solution, right? Then you're going to create a lot, like the rate, you're going to be creating a lot and a lot and a lot of 2NO2. And that is because a high concentration is equivalent to more opportunities for molecules to collide and react. So if you can imagine having a container full of marbles, right? There's a lot of opportunities for the marbles to touch one another and react along the way. But if you have a container that has only like 2 marbles in it, and it's a huge container, then there's a very small chance of those marbles like hitting each other, if they are not like moving on the bottom of the container. If they're like floating around in the air, then it's very hard for them to bounce and contact and bump into each other to react, right? So if you think of the concentration like that, if you think, okay, high concentration, that means a lot of opportunity to react, then it makes logical sense. So does that make sense so far? If you could let me know. So okay, awesome. So yeah, so the rates of each reaction depends on its concentration. Yes, kind of. If you have any questions, feel free to drop them down in the question box. Let me see. Okay, I don't think I have any questions so far. Okay. All right, so this is kind of a picture of equilibrium, what happens. So at time 0, so at the very start, let's say you started off with a jar of solution A. Okay, so that is the blue line, solution A. So you have 100% concentration, let's just call it that. Okay, and you have absolutely nothing of reactant of solution B. Okay. And then what happens is that, okay, so I'm going to actually go back to kind of like show you, kind of like name a reactant A and a reactant B, so you guys can kind of see. So let me see if I can go back. Okay, so I'm going to go back to kind of like show you, kind of like name a reactant A and a reactant B, so you guys can kind of see. So let me see if I can go back. Okay, so I'm going to go back to kind of like show you, kind of like name a reactant A and a reactant B, so you guys can kind of see. So let me see if I can go back. All right, so let's call this the initial solution. Let's call that A, and let's call 2NO2 B. Okay, so this is A, this is B. Also 1 and 2. Okay, so I'm gonna move forward back to that slide. So we have A, which is the one we started off with. So let's say we have everything is A, and then we have nothing of B. So as time goes on for a reversible reaction, we can see that, okay, so we're using up some of A, right? The reaction, A is making a bit of B because it's a reaction moving towards the right. So then you can see that pink line, which represents the concentration of B, also the amount of B, is moving up because you're using up a solution A and you're creating solution B, because you can see that it's like you're creating things, right? And then what happens is over here you can see that the slope is pretty even, like the slope is 0, which means that there's no change anymore in the concentration, and this is where you reach equilibrium. And you can see that the concentration they're not equal to each other, right? So like a lot of people are like, okay, so we're at equilibrium, but we have different amounts of the different solutions. So how can that be equilibrium? Well, the thing is that in a dynamic equilibrium, which is basically another word for equilibrium that we use in chemistry, a reversible reaction when the rate of the forward reaction equals the rate of the backward reaction, which is like rate 1 equals rate 2, or rate of A is equal to rate of B, that is when you have reached equilibrium. So like really the main criteria for you to reach equilibrium is if rate number 1 is equal to rate number 2. So the rate of the reaction moving forward, if it's equal to the rate of the reaction moving backwards, then you have equilibrium. So it's not based on how many amounts. It's not like a scale, right? It's not like you weigh the solution, like, okay, I have this much solution and it has to be balanced. It has to weigh the same as the other side of the reaction. That is not the case. For equilibrium, you just have to make sure that they're basically transferring molecules at the same rate. So yeah, concentrations, they do not have to be equal at equilibrium. And I kind of like to think of it as like a dam almost. So this is actually not the right way the dam works, but I like to think of it as this body of water representing A, okay, and this body of water representing B. And then I like to think of this part as maybe A, okay? So the reaction, I like to think of this body water being A and this body water being B, and then A is starting to react and making more of B, right? So I like to think of this channel as the channel that A moves to B, so it moves this way. The water moves from the right side of the screen to the left. And then I like to think of this other entrance as this body of water moving towards the A. So B moving towards A. So it's moving from the left side of the screen to the right side of the screen. So basically in equilibrium, let's say that this part is flooded, like it is full to the brim, all right? It's not seeping over from the top, but it is full. And this side is super, super low. Like there's barely any water in there. But if the amount that's coming in this gate equals the amount that is coming through this gate, if they're equal, so like the equal amounts of water comes through and goes, then you have equilibrium. So you could have a ton of water on this side and like almost nothing on this side, but if they're transferring equal amounts of water, then you have equilibrium. So if the water coming in is the rate is equal to the rate as the water coming out, then you have equilibrium. So I hope that makes sense. I hope that it gives a clearer picture. So it's really the rate of the reaction that determines if you are at equilibrium or not. All right, so now we're going to talk about the direction of the reversible reaction. Okay, awesome start. is your name Sarthak? I hope I pronounced it right. If I pronounce it wrong, I'm so sorry. I'm really bad with names. Okay, so yeah, so okay, all right, awesome. Okay, so we have the direction of the reversible reaction. Okay, so there's this thing called the equilibrium constant, also called the K. And we also have another thing called the reaction quotient, which is also called the Q. And they're both actually, like, conceptually, they're the same. So it's really just the product over the reactant. This is like a mathematical equation. It's the product divided by the reactant. And the product is in brackets because it represents the concentration of the product. And the reactant is also in brackets because this represents the concentration of the reactant. So if you guys remember what concentration is moles over liters. So it's basically the number of moles per liter of whatever solution you have. So yeah, so that is the concentration. So basically, K, it represents the perfect equilibrium state of the reaction. Okay, and the Q is the present state of the reaction. So basically, how we're going to use these two things is that when we see a reversible reaction, so for every reversible reaction, there's a K that's attached to it, the equilibrium constant. It's basically, okay, this is the value for a perfect equilibrium. This is like a constant of perfect equilibrium for this particular reversible reaction. So for every reversible reaction, they have a different K value, or most of them have a different K value. So K is like the perfect equilibrium. So you know that if you have, oh, actually, you know what? And Q is the present state of the reaction. So basically what you're going to be doing is when you see a reversible reaction, you're going to be plugging in the numbers of like the concentration of the product and the reactant into this equation. And then you'll end up with a Q. So let's say that there's a practice problem that tells you, okay, so right now we have 0.1 moles or 0.1 concentration, or M, of this solution, and then 0.2 concentration of this solution, and then you're going to basically put that in here, right? And then you can see the immediate value. So let's say that so I'm going to go into this a bit deeper later, but let's say that you have a value of Q that is 0.1. Okay, and then the K, the perfect equilibrium for that particular reversible reaction, if it is 0.5, okay, and your Q is 0.1, then that means that you're not at perfect equilibrium. So in order for you to be at perfect equilibrium, your Q value has to match the K value. So I know that's a bit like fuzzy right now, but I'm going to show you guys more examples later. So all of this is actually going to be on the AP equations sheet. So this is what you're going to be seeing. This is the K, which is the equilibrium constant. And then this is another form of the K. This is for gases. So if you're dealing with gas pressures, then you'll be using this. But for the sake of today, we're going to be focusing more on the Kc, which is the molar concentration equilibrium constant. And Kp, honestly, it doesn't appear that much on the AP exam, but it's very, like, the concepts, they're basically equivalent. And also, when you're doing the equations, you do not want to include solids and liquids in the K expressions. So we're going to go over this later more. I'm going to give you guys more examples. Okay, so you saw like the A, the B, the C, the D, all the subscripts. So you might be thinking, okay, what in the world is this, right? So it actually represents a reaction. So let's say you have a reaction that looks like this, right? A, B. So the lowercase a is the coefficient, and the uppercase A is basically the type of molecule you have. And this is the reaction, the equilibrium constant, as I showed you on the previous slide. You can see that the uppercase C, the uppercase letters, they represent the molecule you have, the particular solution you have, and the I guess you could call, what do you call this? Like a subscript? Or no, not subscript. Well, the number on top, it is the coefficient. So I'm going to be showing you guys more examples of this, and also whatever is in the brackets. Remember that whatever is in the bracket, it actually represents the concentration. Okay, so I'm going to kind of show you guys how it all works. Okay, so I'm going to use this example. So you can see that we have this chemical reaction. And then, okay, so I actually made a mistake here, if you guys didn't catch me. So over here, wait, actually, okay, that is really weird. Okay, so yeah, so you can see I used gases here, so it's not supposed to be gases, it's supposed to be like AQ, aqueous solution, aqueous solution. It's not supposed to be G. If it is a gas, then you should be using the other type of equilibrium constant equation. But let's just pretend that it is aqueous solution. Okay. So we have. So you can see here that this is basically the outline for using the equilibrium constant. So so basically, if we were to use this equilibrium constant on this reversible reaction, we're going to see, okay, so what is on the right side of the equation for now? We can see that it's N2O4, right? So we can see that over here, we have the reactants on the bottom, right? So I'm going to put that in, so you put that in here, on the bottom, N2O4. And then you look, okay, is there any coefficients on the front of the reaction of the elements or the molecule? You can see that there's no coefficient. There's not like a big 2 or something or a 3 in the very front, right? So then you have no there's no like power of something. And then you should look at the product side of the reaction, right? And you can see, okay, it is N2O2. So I'm gonna put the NO2 in the bracket, in the numerator, and then you're gonna put a coefficient of 2, and you put it as the power of 2 for this equation. So I hope this makes sense. Does this make sense to everybody? You see how I match it up, and kind of like went off from this general equation and then put it into like basically apply that to the actual, like a real example. Is that making sense? Okay, so I'm gonna move on. Yeah, kind of. Okay, so I hope this becomes more clear as we go on. So remember that the brackets, they represent the concentration. So let's say if we have a 0.01 concentration of N2O4, then we're gonna put that like 0.01 right here. So it's basically, so this is basically like a placeholder for the different concentrations that we have. Why does the coefficient become an exponent? Yeah, that's a very good question. So this is actually part of like a law that they came up with. And so I don't know how to answer that, but I do know that if you were to have like, if you were to double the entire reaction, so if you were to have like two, so let's say you have this whole equation, right? If you double it or something, you have 2 as a coefficient here and the 4 as a coefficient on this side, then we're gonna also change that as well. We're gonna also add in the coefficient of a 4 here and the 2 over here. So, you know, so like so yeah, I don't really know why you do that, but like it is proportionate to the reaction, the reversible reaction that you start off with. Yeah, that's a very good question. I believe that they used many mathematical models to come up with this. Okay, so I'm going to move on and give you guys a practice problem. So this is an easy one. So this is basically our reference equation that we use. And then we're going to write an expression for the equilibrium constant of this reversible reaction. So you can see we have Ti, which is a solid, plus a 2 Cl2 gas, and you can create a TiCl4 liquid, right? So first of all, we need to identify the different the products and the reactants for our equilibrium constant. Okay, so and also remember that we cannot use solids and liquids in the K expressions. They do not count. And that is because they don't react like on the same level as aqueous solutions. So yeah, so if you have like a solid and then you have an aqueous solution, they would react at different rates. Like it just messes it up. So and you also can't really measure these things in concentrations either. Like it's just weird. Like how can you measure concentration of like a liquid when you are using that like that amount of liquid with another like another aqueous solution? It's just like it messes up with the concentration. So you do not want to, so if you do ever see a solid or a liquid in your reaction, in your reversible reaction, then just leave it out of the K expression. So you're going to use, you're not going to give it a number of 0, you just give it a number of 1. So I'm going to show you guys how it's done. So so you can see that this part is the product side, right? And this part is the front part is the reactant side. So so if you remember for K, you can see here that the reactant is on the bottom of the equation, and then the product is on the top. So we know that we want to have this side on the bottom, and then the TiCl4 on the top, right? And so do you guys know what we should do right now? So we should put like each in brackets, right? So we're gonna kind of like designate each part of the reaction to a bracket. So so knowing that the solids and the liquids they should not count, I'm gonna kind of give you guys the answer so you guys can kind of see. So the answer is K. The equilibrium constant is equal to 1 over Cl, the concentration of Cl2 squared. And you can see that we have, so on the top, right, on the top, the numerator, it should be TiCl4. But since it is a liquid, it doesn't count. You should not include that in the equilibrium constant. So therefore, just give it a 1. Okay, and then over here we can see we have a chlorine, Cl2, and we do not have the Ti, right? Because it is a solid, and we do not include that in the equilibrium constant. So, so you can see here that, well, technically you can multiply Cl2 squared by 1, which the 1 is Ti Ti solid, but I just left that out to make it more clear here. So that's basically how we're using it. So you can see again that the coefficient of Cl2, it is used as like an exponent here. All right, so moving on, so we're going to talk about the reaction quotient. That is also the Q. So you can see that it's actually the same, right, as the K. So I'm going to move back another slide. So you kind of compare. So you can see that Kc, it's equal to basically, if you guys can have like a mental image of this, so it's CD, AB, with like its little exponents. You can see it's the same thing here with Q. It's actually the same exact thing. So then, but K and Q, they're kind of used for different purposes. So K is used as the golden standard. It's like the standard of equilibrium. It's like if your Q is equal to K, to the golden standard of K, then you have an equilibrium reaction, right? Then you have your reaction has reached equilibrium. So equilibrium is more of like a state of reaction. It's like, okay, you finally reached the zone of equilibrium, right? It's not like, okay, this reaction is always at equilibrium. It's like it has to reach that stage. So so yeah, so for Q, this is basically like it's like if you guys have ever used a thermometer, right? You can kind of just like plug it in, or not plug it in. You could put it on a surface, and then you can measure its immediate temperature, right? So this Q is kind of the same thing. It's like a tool that just stick it in on into a reaction at any time, and then figure out, okay, what is its value? So, and is this value close to K? Is this value close to the golden standard equilibrium constant? If it is equal to K, then we know that we have, voila, we have reached equilibrium for this reaction. So basically, this is like literally the same thing, right? For Q. So this is how we get the value for Q. And this was something that I was really confused with initially, because I was like, okay, so Q and K, if we have, so what is K used for then? Like why would we calculate K calculate K if K is the perfect standard and is not realistic? It's not like you have a reaction and you use this equation and then boom, you have the K, right? Why do we have the, like, what is the difference between these two? So K, so usually in a practice problem, people will give you the concentration of a reaction, and you need to calculate the Q of that reaction. And they will give you the K. They will just straight up give you the K and say, okay, this is the K of the solution. This is the equilibrium constant of the solution of this reaction. And it's your job to calculate the K, which is the immediate state of the reaction, to see, okay, so is this reaction at equilibrium? So I hope that makes sense. I'm gonna move on to kind of like show you guys a bit more. So yeah, you might have noticed both are calculated with a similar format. It's basically products over reactants, right? And like the way you calculate them both, they're the same too. And when K equals Q, we have each achieved equilibrium. And reversible reactions in closed systems, they always reach equilibrium, or eventually, at least. Sometimes it's kind of like one of those, like, I don't know what do you call it? It's like those like springy things. You know those like stainless steel springs that, like, I think it was like a 90s kid toy. But you basically have these. Yeah, a slinky. Yeah, exactly. The slinky. It's kind of like goes one way and the other and one way and the other. And then eventually, if you leave it long enough, it does come to equilibrium if it's at floor level, right? Or if no one's pulling on it. It becomes that equilibrium. But before it reaches equilibrium, it's gonna lean towards one side and then lean to the other side, and it kind of like it's kind of like bouncing back and forth and back and forth. That's kind of the equilibrium, how it works, right? They will reach equilibrium eventually. And so, yeah, for reversible reactions, they are always working towards equilibrium. It's like a natural tendency for them to want to reach equilibrium, because if you think about it, if a reaction rate of one reaction is going faster than the reaction rate of the backward solution, then it's going to like one part of it is going to run out, and then the other part is going to kind of make up for it, right? So eventually they're going to both like kind of like balance out. Right, so to predict, all right, so this is predicting reaction direction. So I'm going to go back for a sec. So basically, usually you're given a concentration of a reversible reaction, and then you're supposed to tell us if this reaction is going to move towards the right or move towards the left, which means like is the reaction going to move forwards or move backwards? Of course, I mean, it depends on your perspective, right? But yeah, so usually like they'll say, okay, this is called the reactant and this is called the product. Is it going to move towards the right or move forwards or move backwards? What they usually do is they give you a K, right? And then you kind of use the Q to see like where you are in terms of like how close you are to the K, and whether you're above the K or below the K, in terms of the in terms of the magnitude of your constant, or of your value, the Q value. So if Q is greater than K, then K must increase until Q equals K. So I hope this makes sense. So the Q is kind of like what you have right now, your thermometer, right, with your reaction. You're like, okay, so I want to get my temperature, or yeah, my reading of the thermometer of the Q tool to, I want it to be K. Okay, so I'm gonna see, okay, so let's say Q, okay, it's so much colder than what K is. So let's say K, yeah, so let's say it's way below K, right? I need to get it up. Then I know that a reaction, because the reaction wants to reach equilibrium, we know that the Q, it must increase until the Q equals K. So if you can imagine, you're sticking in the thermometer at all times. So it's not like you're just putting it in and taking it out. Okay, if you keep the Q inside the equation, in the solution, the whole time, then you can see that a Q is going to slightly increase until the Q equals K. If you start off with a Q that's lesser than the ideal standard, right? And then if the Q is way above the ideal standard, then it's going to want to come down. It's going to want to lower its value until it is equal to K. And again, equilibrium is existent only when Q equals K. So basically so like if you guys ever have made candy on the stovetop, you know that once you've reached that perfect temperature, you know that boom, you have a candy, you have the candy at the right consistency, right? So when K equals, or when Q equals K, when the current situation of your reaction is equal to the golden standard of equilibrium, then you know that, boom, you have equilibrium. All right, so now we're going to move on to a practice problem. This one's really fun. So basically what we're going to do is we're going to predict the direction of a following reaction. So we have PCl5 as a gas, and interchanged with PCl3 gas plus Cl2 gas. Okay, so, all right, so you have to ignore what I just said about gases. I think I messed up again, because over here, okay, so what I told you guys was that when you use gases, you should use the gas pressure equilibrium constant. I think that's not the case. I believe that's not the case. I think I messed it up here. Basically, if they give you a gas pressure, so that they tell you, okay, this is 1 atm, right? They give you a value that is a pressure instead of a concentration, then you want to use the equilibrium constant that is for gas pressures. But if they don't give you the atomic pressure, then you shouldn't use the atomic pressure equation for the equilibrium constant. So you should use the Kc, the molar equilibrium constant, if they give you a value in moles, or a value in concentration. So, all right, so I'm going to start with concentrations. So let's say that we have, these are all the concentrations that we have to start off this equation. So this is our initial point. This is what we start off with this equation, right? So imagine that you're sticking in the thermometer at exactly this point when we have this much of this. These are basically all the different the amounts of the different agents that we have in this reaction, right? So we stick our thermometer in, we see, okay, this is the current state that this reaction is in. And we know that this is the golden standard, the K, right? The equilibrium constant. This is the golden standard for this particular equation, for this particular reversible reaction. So we know that if our Q is equal to this K, right, then we know that, okay, boom, we are at equilibrium. And so, but if not, then we're going to kind of see, okay, so which direction, how should this reaction move so that it can be, reach equilibrium. So you can see these are concentrations, and then I'm going to move on. All right, so these are 3 concentrations. So the first thing that we should do is we should calculate the Q. Do you guys know why we should calculate the Q? I kind of went over this a bit, but do you guys know why we should calculate the Q? I kind of use an analogy. If you guys have any questions, like why should I calculate the Q first, just like ask it. If it's okay if you don't know why you should calculate the Q first. But I want you guys to understand like why I am calculating the Q and not thinking, okay, maybe I should make an ICE chart to make sure that equilibrium is achieved. Yeah, so Q is like the thermometer, right? We're basically poking it into the solution, kind of seeing, okay, so where are you at right now? Like, what is your Q value? And we know that if our Q is equal to the K, then we know, boom, oh, actually, we're already at equilibrium. We are already at the proper temperature or the proper state of the reaction, right? Yeah, that's exactly right, to make sure that equilibrium is achieved. However, if the Q falls short of the K, if the Q is not equal to K, then we know that, okay, this reaction is currently not in the equilibrium zone. It is not at its equilibrium state yet. So, if you remember, if you were to set up the equation for Q, which is equal to C, but you can see that it is, you take the product side and you put it on the numerator, right? So you can see over here, we have everything on the numerator side. So the products, PCl3, we put it in here, Cl2, we put it in here. And you can see that if you're adding, if it's like a plus sign right here, you just put it in as a multiplication problem right here, right? It's not like you have a plus sign in between these. You multiply them, and that is because I'm going to kind of move backwards to the other side that I have. You can see here that there's no plus sign, there's no addition sign or subtraction sign. It's all multiplication. Okay, so I'm going to move on to where I just left off. So you can see that on the denominator we have the reactant, and in its concentration form, so in brackets. So if anything is in brackets, you know that it is asking for the concentration, right? So we're going to first plug the proper solutions in, the proper names for the solution, so we know that we are matching it up correctly, because we don't want to mess it up. And then we're going to put in the concentration values, right? So we know that PCl3 is 0.06. So you can see we put it in here. And then Cl2, 0.05, we put it in here. And then PCl5, it's 0.05, and we put it in here on the denominator. So you can see that this is, so you basically plug it in like that. So it's basically, yeah, you just put in the concentration and just plug it straight into the reaction that you have, or the equation that you have for Q. And then once you calculate that, oops, sorry, I have this thing blocking the way. So once you calculate that, you can see that Q is equal to 0.06. And if you put it into scientific notation, it is 6 times 10 to negative 2 power. Or actually, if you were to really be specific, it would be 6.0, I believe. Yeah, 6.0 times 10 to negative 2 power. So you can see clearly that K does not equal Q, right? Okay, sorry, I just blocked it again. Yeah, so you can see that K is not equal to Q. So the current state of our reaction, so if we stick the thermometer into this solution at this point, at this stage, you can see that, okay, it is not equal to Q. The reading for this value is not equal to K, right? It's not equal to the golden standard. So therefore, we know that we have not achieved equilibrium, right? Because Q is not equal to K. All right, so our next question is, how do we figure out which direction the reaction should move so that we can achieve the equilibrium state? Do you guys have any ideas as to how we can figure out like which direction this reaction should move? So left, okay. Okay, and why do you think left? So I'm gonna keep moving so that like you guys can kind of see. So it's because of the nature of the Q equation, right? So what does the Q equation tell us? The Q equation is basically, so if you remember, it's basically the products, right, over the reactants. This is a division problem, right? Maybe by using a difference of the reactants and the products. Yeah, so by difference, do you mean like the moles of one side versus the moles of the other side? Like how the amount of one side versus the amount of the other side? So if you remember, when I talked about equilibrium, I don't know if you were here when I talked about like the part about concentrations being equal during equilibrium. So when you're at equilibrium, you do not have to have both sides of the equation be equal in terms of concentration. I was actually thinking subtracting, but your method may actually be better. Okay, so subtracting. So how do you think you should subtract? Sorry if like I'm like pushing you here, but like I think you can't subtract because like do you mean like making an ICE chart and then like subtracting different values and then kind of like or subtracting equal values off of the whole equation? So I think that like that is effective for figuring out like if you want to add something or if you want to remove something from everything. But if you think about it, if you remove the equal amounts of moles from every single part of the equation, so if we remove 0.1 moles from here, 0.1 from here, and 0.1 from here, then then it's not really changing the dynamic of the equation. It's just like, okay, everyone just got reduced a little bit, but we got reduced proportionally. So we still have the same speed of reaction, right? So what I initially talked about for equilibrium is that you do not need equal amounts of product and equal amounts of reactant to be at the equilibrium state. Okay, so the only criteria for you to be at equilibrium is if the reaction from the action right, the reaction forward like this is equal to the reaction backward like this, right? So if the reactant, so since equilibrium is about reversible reactions, which means you can see that there's funky arrow here, which means that the reaction goes both ways. It's like reversible. It's like it doesn't just go from the left to the right. It also goes from the right to the left. That means that there's a reaction going both ways. There is technically this whole thing. It represents two reactions. It represents the reaction going right and the reaction going left, right? So the only criteria for you to be at equilibrium is if the rate of reaction, so the speed at which you are moving, the speed of the reaction forward is equal to the speed of the reaction moving backward. So if you can imagine this, we have two big water tanks, which I had a slide for earlier on. You have two big water tanks. And one water tank is super, super, super small, right? The other water tank is super large. And then one water tank has a ton of water, and the other water tank, the small water tank, has like a tiny, tiny, tiny bit of water. But let's say that the amount of water that's transferred, so let's say that both water tanks are connected through a tube or through two tubes, okay? And one tube moves water from one container to the next, and the other tube moves water backwards, right? Let's say that the equal amounts of water are moving from both ends. So it's like they're crossing, right? If they're moving at the same rate, then you're at equilibrium, even though you have different amounts of water in both water containers. I hope that makes sense. I can go over that. I can like find my slide for that later. If you would like to see a better visualization of what I just said. I know it's like a kind of weird thing to wrap your head around, but really equilibrium is about the rate. The rate of reaction is so, so, so important. And I'm gonna go over it a bit fine. Okay, oh, it's fine. All right, awesome. Okay, so we can see here that Q, so the Q that we just calculated, it is much bigger than K, right? You can see that 6 times 10 to the -2 power, it is greater than 1.6 times 10 to the -power. So we know that K is greater than Q is greater than K, which K is the golden standard, right, of equilibrium. So our next question is, how can Q become equal to K, which is essentially a rephrasing of how can this reaction reach equilibrium. So I think Seamus, I hope I'm pronouncing your name right, Seamus, he said move the reaction, he says that the reaction is going to move left. Oh, Seamus, okay, sorry, Seamus, all right, nice. Yeah, so he says that the reaction is going to move left because the reversible reaction, it has a tendency to reach equilibrium. So it wants to reach equilibrium, right? So it's going to naturally, so Seamus says it's going to naturally move to the left. So the reaction is going to move backwards, so that we can reach equilibrium. So okay, so remember the K and the Q, they're all calculated through this general type of equation where the product is divided by the reactant, right, which is on the bottom. So that means that if Q is greater than K, then the Q, let's pretend this side, this is the Q, okay? This whole reaction is equal to Q. That means that we have a ton of product and very little reactant, right? Compared to the K, which is this, which is like, or actually, you know what? This is not a perfect representation, but let's pretend that this is a good representation of the K at its ideal state, right? If you were to actually like compare the different concentrations, this might be a 10, this might be a 1, but like let's pretend that this just represents the perfect equilibrium. Then this, which is the Q, which is compared to the perfect equilibrium, you can see that Q has a big product, a lot of product, but very little reactant. So what we need to do is we need to make the reactant bigger, right, or decrease the product, right, in order for this to be equal to the K, the golden standard for equilibrium. So what will happen if we what kind of reaction does there need to take place for the product to become smaller, or the amount of product to decrease? So I think Seamus already said this, which is awesome. So he says that the reaction should move towards left, right? And so if the reaction were to move to the left, that means that this side, so that means that it's going to move backwards. So it means if you follow my red pointer, it's going to move this way. So that means that this side is going to start reacting a lot, like it's going to start using itself up so that it can produce more of PCl5. And so that means that a product is going to start working so that you can create more reactant. And that is exactly right. So the product is going to start working, it's going to start using itself up so that we can create more reactant, right? And then that is exactly how the Q is eventually going to reach the K, the golden standard, the golden ratio for equilibrium. Okay, so I think that is all the slides that I have for today concerning equilibrium. Do you guys have any questions about equilibrium? So I hope that like this picture of like the product and the reactant, I hope that made sense, kind of like clarified some things for you guys, because like I know that for when I learned chemistry, when I saw like, oh whoa, the product is so big, right, or the the visualization of seeing the product being this big, it kind of puts into perspective, like, okay, so I need to decrease the product so that I can have the right ratio for K. And it's literally like, this is literally just a visualization of like what is actually going on, because like literally if you were to go back, if I were to go back to the concentration, you can see that the reactant, you can see that the reactant, it has a really high concentration. The product has a high concentration. All right, so Mafu says, oh, so I can write it down and understand it better. Could you repeat how Q can be equal to K? Yes, so basically, right, so what you do is you use the Q equation, which is what we just used, right? We use the Q equation, which is right here. We use the Q equation to find out its reactant quotient. I believe, yeah, reactant quotient to find the Q value. So, um, wait, so are you asking about like um, how how you can tell where the reaction is going to go for Q to be equal to K? Because like honestly, like when you calculate this, it's not like you're trying to move the reaction in some way. It's more like you're trying to predict where, like which direction the reaction is gonna go. Because we as humans, we're not actually doing anything. We just understand that okay, this is a reversible reaction, so it has a natural tendency to become to reach equilibrium. So like knowing that fact, knowing the fact that okay, it wants to reach equilibrium, then we can better understand where the direction, which direction the reaction is going to head, so that it can reach equilibrium, if that makes sense. I'm going to move on to the last side. I think what you wanted to see is on the last side. Oh, so for this particular reaction, Q can be equal to K if its product starts to decrease. So you can see over here, this is Q. This is the Q that we have calculated, because as you can see here, Q is greater than K, right? So that means that in terms of math, it means that the product, the numerator is huge, and the reactant is very small. Or even like you don't even have to think that the product is huge. You can just think that okay, the reactant is very, very small. It's not enough to reach K, to reach the golden standard of K. And so therefore you want to make sure that you decrease the product and you increase the reactant. So you basically, so that you can level it off. Oh, I was thinking that there was a process to go through in order to make them equal. Yeah, no, there's actually no process. Like this is literally, it's like a thermometer, right? So let's say you're baking turkey, right? You stick the thermometer in and you can see, okay, is this turkey cooked or not? And then if it's not, then okay, then I need to cook it a bit more. But then if its temperature is like way up there, right? Then you know, okay, I probably overcooked it or it's gonna burn soon. So it's literally just like this. It's like we're trying to reach that perfect sweet spot of the equilibrium, and we're trying to see, okay, should this reaction move forward so that we can create more product, or should the reaction move backward so that we can create more reactant in order to balance it off. And we also have to remember that if the reactant were to move one side, then the reactant is going to be used up. So if we're moving forward, we know that the PCl5 is going to be used up. It's going to the amount of this is going to be used up, so it's going to decrease as the reaction goes, and then there's going to be more of this, the product side. So yeah, it's literally like you're trying to get to that sweet spot. So it's like, okay, sometimes you make too much of products, oh, and sometimes you make too much reactants, and then you try to like balance it off, and so that you can make so that the speed or the reactant, the reaction rate can be equal. And like I said earlier, let me see if I can move to an earlier slide. I think it's, let's see, I don't know if I'm right. Okay. What was I gonna say? I was gonna talk about the rate. Hold on, I'm gonna move to the last slide, see if I can remember what I was thinking. Yeah, so yeah, it's literally, okay, I remember. So the reaction rate, so you probably are confused. You're like, okay, so like we're talking about concentration, but we're also talking about reaction rates. So the thing is that the concentration determines the reaction rate, right? So if we have if we have a high concentration of something, that means that its reaction rate is going to be high. If we have a low concentration of something, that means the reaction rate is going to be low. And usually I don't like to compare it, I don't like to compare, I would not recommend comparing PCl5's concentration to Cl2's concentration and see, okay, which one's going to react faster. No, I usually like to compare them to themselves. So let's say that we had 0.01 concentration of this, and then we have 10 concentration of this, right? Then we know that, okay, so 10 concentration, okay, that means that this is going to be producing much, the rate is going to be much faster than the rate at which you had a lower concentration. So I think I talked about this a bit earlier, is that I like to think of concentration as like a container. If you have high concentration, that means there's a ton of marbles or ton of things inside, right? That's going to bounce around. They're going to hit each other a lot. They're going to hit each other very frequently. And so that means you have a lot of opportunities for reacting. You have reactions going on at a high speed because there's so many different reactions. It's reacting so fast, right? It's bouncing to each other. They have lots of opportunity to bounce into each other. But if you have a low concentration, that means that you don't have much to work with initially. So therefore, the rate of reaction is going to be slow. You're not going to bounce into each other that much. And concentration, the equation for concentration is literally moles divided by liters, I believe. Yeah, moles divided by liters, which is amount per volume, right? Amount per volume. So if you think, okay, so I have a huge container, but I have just tiny bits of moles, tiny bit amount of the actual reactants in there, then it's going to be a huge open space, but very few opportunities to actually react with each other. So yeah, anyways, that was a bit of a tangent. That's kind of how I like to think of reactants and the reactor rates, and how I like to picture concentrations in relation to the speed of reaction. Okay, so Seamus just asked a question. He asked, is Fiveable's AP Chemistry sufficient to learn the course, or should I supplement with other resources? Yeah, that's a very good question. I think Fiveable's AP Chemistry, I think, is very sufficient. I think, so we're having more live streams in the future, and I think that if you do attend all of them, you will have a very good base knowledge in AP Chemistry. I will say that to prepare for the AP Chemistry exam, you do need to be doing some practice problems, but honestly, it's not necessary until April. So you do not need to be doing it right now. I would say probably I would say go on College Board and go on the AP Chemistry page and then look at the FRQs, the free response questions. Okay. And if you go on free response questions, you can see all of the free response questions from last year and from the years before. And then you can kind of see, okay, how do they structure their questions? How do they ask their questions? What kind of questions do they ask? And then also look at the rubric. I would say the most important thing, though, is to look at the student answers. Because here, let me see if I can share I don't think I'm allowed to show you guys College Board material because it's copyrighted. So I can't share it here. But if you go on College Board, they do have you go on the exam preparation, the FRQs. There's this part called the sample student responses part, and if you click on that, you can see literal answers that past students have written, and you can kind of see, okay, so this is what they want to see when you write down your answers on the sheet of paper, right? This is exactly the format they want to see you follow. And for me, when I prepared for AP Chemistry, that was the most helpful thing. When you're first practicing for FRQs, it's so stressful. I don't know if you guys have already practiced or started practicing FRQs, it's very it's very stressful. You're like, okay, there's so many like criteria I have to meet. I have to write down every equation. I have to be very thorough, right? And it's also the time constraint. Oh my word, it's you have to work so fast, right? But like if you look at the student responses, you can see what their favorite response looked like. And you can see the student, usually they didn't write like a ton and ton and ton. Like they weren't super elaborative. Like they wrote enough so that like it covered everything that the AP exam graders wanted to see. And I would say just review those answers and really understand how they wrote them. And actually, I wrote a guide to AP Chemistry's FRQs that's going to be published soon on Fiveable on the blog, I believe, or I don't know if it's a blog. It's a guide. Yeah, so I'm gonna be I wrote a whole like guide to FRQs, and it's basically all the tips that I've accumulated. And so yeah, definitely. So I would say like definitely do check out FRQs. They're not good. They're not just for practicing FRQs. They're also great for understanding AP chemistry material, right? So it's really interesting. Like you look at the rubric and then you actually learn AP chemistry along the way. So if there is an FRQ that you're just so scared of, like, oh, you're like, and you read it over, you're like, okay, I have zero clue how to answer this. Then you just look at the answer key, just look at how they answered it, and then see, okay, so that's how they reason through it. And College Board also has a rubric, so they have like basically a whole answer key, and you can see, oh, so College Board says that for gas reactions, this happens. So then you just kind of like it's like a great review session, and also it's good at explaining things. And especially is so good at patching up the rough spots you have in AP chemistry, because I know for every single unit you probably have certain topics that you're a bit iffy about. And when on FRQs, like those fears, they like if you don't know something, you can't really make something up. I mean you should definitely still try, but like where your weaknesses are when you come to the FRQs. And so yeah, so the College Board FRQs, they're very elaborative. Their rubric is very elaborative, and if you look at the student answers, you should be all set. So yeah, that's basically the tips I have for supplementation. Yeah, and also I will recommend, if you guys watch YouTube videos for AP Chemistry help, I highly recommend Professor Dave Explains. His videos are so good. Like I remember being so stuck on acids and bases, and I watched one of his videos. It was like 3 minutes, or yeah, it was like 3 to 5 minutes, and then he explained like everything that I didn't understand. In a matter of 5 minutes, or 3 minutes actually. So actually I'm gonna search him up. Professor Dave Explains. I'm gonna link his channel to this live stream so you guys can find him. His videos are so nice. Like with most YouTube videos, they're either too simple or they're too entertaining. Like they're either too entertaining or they're too dry. Like you're on there and you're just like, okay, like this, it's like a blackboard teaching, and it's just not engaging at all, and you can't remember anything, or it's just not interesting enough to keep you engaged. But Professor Dave, like I highly recommend, and for like every concept that you want to learn. Professor Dave Explains. He also uses example equations as he goes, so it's never just conceptual either. Okay, so I think I have the button on here. Do you guys see the button? It says Professor Dave Explains. Yeah, it's like this blue teal button they should see. Yeah, that is Professor Dave Explains. And I highly recommend you watch some of his chemistry videos, especially if there's a subject or topic that you just have trouble with, right? I bet that he can answer it within a few minutes, especially if it's something that's very fundamental. So if it's something like, okay, I don't understand like acid and bases at all, then watch this video and you're gonna be you're gonna come away from it like having a much deeper understanding of like how it all works, and you'll enjoy chemistry a lot more too if you use his resources. Okay, so all right, so that is all I have for today. Do you guys have any other questions for me? If not, we will see you in our next live stream. Hopefully, I think we're currently planning on having more AP Chemistry live streams. We don't have any. I don't think we have any scheduled yet, but we do have more coming. So, and also, if you're taking other AP subjects, please do check out our other AP live streams. They're super helpful. And I wish you guys the best of luck in your studying, and I hope that you guys will enjoy AP Chemistry. And it is February. It's almost April. It's almost May. So you guys can do this. AP Chemistry, if you've already gone over acids and bases, you'll be like, it's not gonna get much harder from here. Like, yeah, like I literally loved every part of AP Chemistry except for acids and bases. That part was a bit intimidating. But yeah, so do you guys have any other questions? If not, I'm going to call it a day. And thank you guys so much for attending this live stream. And I hope to see you guys in other live streams and see you guys around. So thank you for coming. Bye. Have a great rest of your week.